And I did record those lectures last week and posted those in Blackboard. So the chapter, sections 4.3 through 4.6 have been posted in Blackboard in announcements. So you can find those lectures. All right, so we are going to start, though, with a review of chapter 4. However brief, we are going to review. All right, so in chapter 5, we're going to introduce continuous random variables. So this starts our discussion of all the different continuous probability distributions. But before we do that, let's talk about discrete. So in chapter 4, we looked at discrete probability distributions. And the two characteristics of a discrete probability distribution is that each probability, so the probability that your random variable takes on a particular value, has to be between 0 and 1 inclusive. And the other characteristic is that when you sum all these probabilities together, you get 1. So I went into Excel and I created a discrete probability distribution. Now, again, the probabilities, the random variable takes on, in this example, values between 0 and 20. So a discrete probability distribution, the values that your random variable takes on are values you can count. So, for example, if you have 10 marbles in a bag and 5 of them are blue and 5 of them are red, if you take out marbles from this bag randomly, you can count the number of marbles you have. So if you can count the values, then that's discrete. All right, so in this particular example, I don't even really remember what distribution I used to create this example, but the random variables can take on values from 0 to 20. And if we were to add all these probabilities, these 20 probabilities together, we would get 1. So the probability that my random variable can take on the value of 0 is 0.0000261. The probability that my random variable can take on the value of 1 is 0.000363, etc. And I can actually graph this distribution using a histogram, and I can see what the distribution looks like. So the horizontal axis of this distribution are the values that my random variable can take on. So my random variable can be 0 with a probability of 0.0000, did I get enough zeros? To 6. So the vertical, the height of this bar, represents the probability that my random variable can take on the value of 0. So this looks very much like a frequency distribution, which we did way back, whatever chapter we did that in. So we did this already. It looks like a frequency distribution, and that is what a discrete probability distribution is. So this probability over here in the second column is the frequency, the number of times that 0 would occur. That's what it is. So if you were to want to calculate one variable statistics on this, you could. So you can find the mean and the standard deviation of a discrete probability distribution when it's in this table form by just putting this in your calculator. And you had a problem in section 4.1, 4.2 homework where you needed to do this. It was what? One column was claims and the second column was probability, the probability. So if you put the first column, the values that your random variable can take on in L1, and you put the second column, the frequencies or the probabilities, in L2, then you can calculate the one variable statistics on this by, on your calculator, going to the stat menu and then going to calculate. And then number one is one variable statistics. And you can calculate the mean of this distribution and the standard deviation of this distribution doing that. And that's way easier than doing it any other way. The mean of a discrete probability distribution can be found by taking the sum of the values of your random variable times the probability that you get that random variable. So you could actually multiply the first column times the second column, get a product, and then add all those products together and get the mean. So you could do that. It's just way more work than you need to do. So you can put it in your calculator and find the expected value or the mean of your distribution. And the standard deviation is way more complicated, and you certainly don't want to do that by hand. So put this in your calculator and let your calculator calculate it for you. All right, so we looked at 4 discrete probability distributions, and each one of them has their own, what they're applicable to. So the first discrete probability distribution we looked at was the binomial distribution. And the binomial distribution, bi means 2. So you either get a success or you get a failure. You get one or the other. So if I have a bag of 10 marbles where 5 of them are red and 5 are blue, what's the probability that I get a blue one? Well, that's the problem. If a success is getting a blue one and a failure is getting a red one, then that could be binomial. So binomial distributions, you either get a success or you get a failure, one or the other, 2 choices. Now, a geometric, you also have success or failure, but the difference is you're not considered successful until you get the value you want. So fail, 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 till you finally get it. And that would be a geometric. And both of these you can do on your calculator. And on your calculator, if you go second, I forgot what, it's above the variables button, right? Variables. Above that is your distributions. And you can find those 2 distributions in that menu. And you've got 2 types of binomial and geometric. You got binom PDF and binom CDF. And the binom PDF, you're going to find the probability of the random variable being exactly a number. So for example, if you were trying to find the probability that x equals 1, you would use binom PDF. And the binom CDF finds the cumulative, and it finds cumulative less than or equal to. So if you were trying to find the probability that x is less than or equal to 2, for example, you would use the binom CDF. So those are the distributions. And you have the same for the geometric. You got geometric PDF and geometric CDF. So those 2 discrete probability distributions are on your calculator. Now, the hypergeometric, this is when you have 2 samples. You're choosing from 2 different groups, not 2 samples, 2 different groups. And you're interested in the probability of getting something, for example, what was the example you had in the book? You have like a bag, and you've got inside this bag, I don't know, 20 red and 30 blue marbles. And you're interested in pulling out a sample. So let's say I'm going to take a sample from this bag of 10 items, 10 marbles, and I'm interested in getting exactly 10, not 10, well, 10's fine, 10 red marbles. What's the probability that I pull 10 marbles out of this bag and exactly 10 of them are red? That's a hypergeometric. And a hypergeometric is not on your calculator. And I'm not sure why it's not on your calculator, except that you can use a formula for it. But you can use a formula for the binomial and you can use a formula for the geometric. So I'm not sure why TI chose not to put the hypergeometric on your calculator, but it isn't. So the easiest way to do this is using Excel. And I show you on the video I recorded last week exactly how to put it in Excel. It's really easy to do, to put it in Excel, but you have to have Excel on your computer. So if you don't have Excel, remember that Redlands will offer it for free. You can get it for free through Redlands. And you simply go to the support icon in the upper right corner of My Redlands, which is the little light bulb. And then you just click, I want Office 360, and they'll send you a link and you can get Office 360. So it's really easy to get and it's free, doesn't cost you any money. So if you don't have Excel, I would go ahead and do that. You get Word and PowerPoint and everything else with it also. So those are probably things you're going to need, especially if you're a freshman. You're going to need those things as you move on in your career. So you might as well get them from Redlands for free. Again, it's not on your calculator, the hypergeometric. So you will need to use Excel, or in the video and on your PowerPoint slides. Did I put that on your PowerPoint slides? It may not be on your PowerPoint slides, but there is for it. And you can get that from the video. There's a combination formula that you can do. And I show you how to do it in the video. And then the last discrete probability distribution in chapter 4 is the Poisson. And this is one, if you're given the number of events that occur in a fixed interval of time, then that will be Poisson. So if they tell you that on average you get 10 phone calls in an hour, or on average you get 50 texts a day, or if on average, but if they give you an on average, this occurs in this period of time, then you know it's Poisson. And I think probably the indicator, the strongest indicator that it's Poisson is this right here. If they tell you that something occurs over a period of time, you know it's Poisson. And if it's Poisson, again, that's on your calculator. That's one of the distributions that you're given on your calculator. You're given the binomial and the geometric and the Poisson, and then there's a whole bunch of other ones that we're going to be talking about as the semester goes on. All right. What was I going to say about the Poisson? I think I was going to talk about, and I do talk about this in the video, at most and at least. And at most means less than or equal to. And at least means greater than or equal to. Now, if they say find at least x equals 4, so you're trying to find x is greater than or equal to 4, the cumulative probability on your calculator is less than or equal to. So what you would be given if you put in 4 is that. And if you're looking for greater than or equal to, you're actually wanting to the right of 4 and equal to 4. So what you're actually interested in is that, and what your calculator gives you is that. So to find greater than or equal to 4, what you do is you subtract from 1 the probability that x is less than or equal to 3. And that'll give you the probability that x is greater than or equal to 4. So you take 1 and you subtract off everything to the left of 3. And that will give you everything to the right of 4. Now remember, this is discrete. That means you're counting these. So greater than or equal to 4 is actually 1 minus less than or equal to 3. And your calculator finds less than or equal to 3. It finds the cumulative probability for a value less than a particular value. It doesn't find greater than, it only finds less than, or it finds exactly equal to. So PDF is equal to a value and CDF is less than or equal to a value. I know there was a couple of questions I got via messages in my Open Math that asked these type of questions. And by the way, if I know a lot of you have used that, if you haven't used that, and I can't remember exactly what it says in my Open Math, does it say contact your instructor or something like that? I don't remember.
Yeah, it says message your instructor, and then it'll send the exact problem to you.
And that's exactly what it does. So when I go into, I go into my Open Math through the back end, because then I can, take care of due dates and grades and all that kind of good stuff. So when I go in the back end, it just tells me as soon as I go in, I've got messages. And then I can click on the messages and it tells me who sent it and what problem it is. So even if you don't type any issue you have with a problem, I know what problem it is. And I can take a screenshot of that, put it into my notepad on my iPad and send you back information. And it works really well for me. I don't know how well it works for you, but several of you have utilized that. So if you have an issue with a problem, whatever it is, you can't get the answer, then utilize that and just tell, and I will send you back a PDF with a hints or a solution. Depends on what mood I'm in, how far I actually answer the question. But that's a really good way of letting me know that you're having problems with a particular problem. All right. All right. So let's now start continuous random variables. And the difference is, chapter 4, we looked at discrete. So data that you can count. And continuous, remember from chapter 1, continuous means data that you measure. So discrete, you count it. Continuous, you measure it. So continuous random variables have many applications. Baseball batting averages, IQ scores, the length of time a long distance telephone call lasts. Do we even worry about long distance telephone calls anymore? Believe it or not, fun fact, my husband, we still have a landline. And my husband just took long distance off that landline. Do you know the last time I made a long distance call from my landline? Probably 10 years. He finally took it off, so we don't pay for that anymore. Anyway, the amount of money a person carries, the length of time a computer chip lasts, and SAT scores. These are all examples of continuous random variables. And we'll talk about just here in a second what the difference, how you can tell the difference between it being continuous and it being discrete. The field of reliability, so how long things last, depends on a variety of continuous random variables. So here we are. The values of discrete and continuous random variables can be ambiguous. For example, if x, the random variable, is equal to the number of miles to the nearest mile you drive to work, then x is a discrete random variable. You count the miles you drive to work. If x is equal to the distance you drive to work, distance is something that you measure. So you would measure the values of x, and x would be a continuous random variable. So if I just count the number of miles I drive to work, discrete. But if I measure the number of miles to work, then that's continuous. For a second example, if x is equal to the number of books in the backpack, your backpack, then that's discrete because you would count the number of books you have in your backpack. But if you weigh, so you have the weight of the books in your backpack, that would be something you would measure if you weigh something. So that would be continuous. If you measure it, it's continuous. If you count it, it's discrete. So here's a really wordy slide on the properties of continuous probability distributions. The normal distribution is a continuous probability distribution. For example, the graph of a continuous probability distribution is a curve in the coordinate plane, and the probability is represented by an area under that curve. The curve is called the probability density function, abbreviated PDF. Could we use a different abbreviation? PDF, probability density function. And we use the symbol f of x to represent the curve. So this is notation that we got back in algebra. So what does this mean, f of x? We'll talk about that some more in just a second. So if it's been a while since you took algebra, or if you just need a reminder, we'll remind you of what that notation means in just a second. We use f of x is the function that corresponds to the graph. So again, as you recall from algebra, whenever you took algebra, if you have a coordinate plane, so you have a plane, piece of paper, and you draw a curve on that piece of paper, you can describe that curve using an equation. And that equation that you use is this thing called f of x. We use the density function f of x to draw the graph of the probability distribution. The area under the curve is given by a different function called the cumulative distribution function, abbreviated CDF. The cumulative distribution function is used to evaluate probability as area. And guess what? You don't have to do this. Either your calculator is going to calculate the area for you, or it's a really simple area for you to calculate. It'll be rectangles. So the area under a curve represents the probability. And that curve is described using a function, an equation. And you would have to use methods that we don't have to be able to find the area under that curve. All right. Area under the curve is given by a different function called the cumulative distribution function, abbreviated as CDF. The cumulative distribution function is used to evaluate probability as area. The outcomes are measured, not counted. So the outcomes of an experiment are something you measure, unlike a discrete probability distribution where the outcomes are something you count. The entire area under the curve and above the x-axis is equal to 1. So just like in a discrete probability, the total probability is 1. In a continuous probability distribution, the area under the curve, the total probability is equal to 1. Probability is found for intervals of x values rather than for individual x values. So in a discrete probability distribution, I could find the probability that X equals 2. So for example, I have those red marbles and blue marbles in a bag. I draw 5 marbles out of the bag at random. What's the probability that exactly 2 of them are red? So that's the probability that X equals 2. You can do that with a discrete probability distribution. With a continuous one, you cannot. You're going to be finding probabilities from a value to a value. So what's the probability that X is between 2 and 5? But you can't find the probability that X is equal to 2 when you're using a continuous probability distribution. So the probability that X is greater than C and less than D is the probability that the random variable X is in the interval between the values C and D. So what's the probability that X takes on a value somewhere in between those two? And that is the area under the curve above the x-axis to the right of C and to the left of D. So it's the area under the curve between C and D. The probability that X equals a value C is 0. The probability that X takes on a single individual value is 0 when you're talking about a continuous probability distribution. The area below the curve above the x-axis and between axis C and axis C has no width and is therefore has no area. So the area is 0. The probability is equal to the area. The probability is 0. Okay, so again, continuous probability distributions. We can find the area that represents probability by using geometry. If it's rectangles, you can. Formulas, technology, yay, technology, or probability tables. And we are going to use technology. We're going to use our calculator to find the probability under these curves. In general, you'd have to use calculus. So to find the area under a curve, you would actually integrate in calculus. Okay, raise your hand if you want to integrate. Maybe if you move on into calculus, if you take business calculus or calculus, both of which I teach, by the way, online. So if you want to take business calculus or calculus in your future, that would be me. When we use formulas to find the area, in this textbook, the formulas were found using techniques of integral calculus. However, because most students in this course have not studied calculus, we're not going to be using calculus. You're welcome. There are infinite, it says there are an infinite number of continuous probability distributions. There are an infinite number of normal distributions. So there are a bunch of them. So when using a continuous probability distribution to model probability, the distribution used is selected to model and fit the particular situation in the best way. Just like in discrete, you used one of those 4 distributions that fit your situation. All right, so continuous probability functions. Let's review what a function is, especially if it's been a while since you took algebra, or if it's been a while since you took college algebra at a college. So let's review what a function is. And functions are so incredibly important. And I think I try to, in college algebra, emphasize how important functions are, especially for students. If you take college algebra, there's an assumption on my part that you're moving on in STEM, because that's the course, college algebra, that leads you to STEM. If you're not going on in STEM, then you should probably take something else. Or if you're nursing, you can take college algebra. But normally, if you're moving on in STEM, that's the base course for moving on in STEM. It's the base course to take trig, take calculus or business calculus, etc. So what is a function? A function is a correspondence from a first set, and we call that the domain, to a second set, which we call the range, in such a way that each element in the domain corresponds to exactly one element in the range. So if we set up, let's draw a picture. And let's call this the domain. And let's draw another blob. And let's call this the range. Then if I have an element in the domain, which will represent the element in our domain as a point, and we have an element in the range, then a function is a correspondence from one element in the domain to another element in the range. And normally we call this x. We use x as the stuff in the domain. We call the function f or g or whatever value, whatever variable you want to call it. And then we output something in the range, which we call f of x. So a domain is just a correspondence between something we call x and something we call f of x. And normally we write this correspondence as an ordered pair. And we use parentheses. And the first value in our ordered pair, we separate the two values using a comma. And the first value in our ordered pair is whatever we have in the domain. And the second value in our ordered pair is whatever we map to, whatever we correspond to in the range. And you can only have one x going to one f of x. X can't go to more than one value in the range. That would not be a function. So you have a correspondence from some value in the domain to exactly one value in the range. That's what a function is. That's all it is. So correspondence between two values, one value's in the domain and one value's in the range. Now, typically, when we describe a function, we use an equation. And that kind of sort of makes sense, because if you're taking an algebra class, wouldn't you expect that you would use an equation? And what's an equation, by the way? What makes something an equation is equals. So as soon as you write something and you have an equal symbol in there, it's an equation. So we write something like, f of x equals x squared plus 5. I don't know, just made something up. So this is the way you would write a function as an equation. And what does a function do? A function takes some value x, inputs it, plugs it in, and then outputs some value. That's all a function does. So what can you input here? What number can you square and add 5 to it? Anything you want. So, I can take any value in the real number system, any number that I'm familiar with, square it and add 5 to it. So you would say the domain is anything. It's a set of all real numbers. And then the range is the stuff you output. So the domain is the values for x. And in our case, it could be anything. And then what's the range? The values for f of x, whatever those are. So for example, if I plugged in 0, so now my input is 0. what do I output? I output 5. So if I were to draw a picture, 0 goes to 5. And that's what a function is. All right. Now, not every equation defines a function. And the fact of the matter is, if you solve an equation for y, I should say that too, y and f of x mean the same thing. So often you'll see that if you are on the coordinate plane, you have an x and you have a y. Well, y and f of x are exactly the same thing. So why do we use that fancy notation? Because if we use the fancy notation f of x, you know it's a function. That's all. That's the only reason we use it. So not every equation you get defines a function. And we're not concerned with, in statistics, we don't care, because we're going to be given an equation that is a function. But just be aware, it's somewhere in the back of your mind, you're going to lose this as soon as we stop talking. But there are equations that are not functions. Okay, so what does a function do? Function takes some input from the domain. It puts it in this machine and it manipulates it. So the function f manipulates my input x and it outputs some f of x. That's what a function does. Okay, so what's a continuous probability function? Again, it's an equation that describes a curve. So if I write this, that is a curve in the coordinate plane. And the coordinate plane is just where we have two axes that are perpendicular to each other. One is horizontal and one is vertical. And y and f of x are exactly the same thing. And f of x equals x squared is just a curve in the coordinate plane. That's all it is. So if we define a continuous probability distribution function using an equation which represents a curve, these functions we study are special, and we define the probability as the area between the equation of this function and the x-axis. So in this particular case, let's just draw this part of it. This function looks like this. And if we were interested in the probability, let's call that A, and that 0. If we're interested in the probability that our random variable takes on a value between 0 and A, that would be the area under the curve. That's by definition. And how do you find that area under the curve? You would use calculus. You would integrate the equation from 0 to A. I don't want to do that. Actually, I love to do that. I love integration. I think it's fun. But what you would do is you would integrate that function between 0 and A. But we don't need to do that because we're going to be given methods for finding the area under the curve, either using geometry or using our calculator, one or the other. Since the maximum probability is 1, the maximum area under the curve is also 1. So for continuous probability distributions, probability equals area. And it's the area between the x-axis and the curve. So let's consider this function. F of x equals 1 over 20. So, and we're going to stipulate that the domain of this function is any value between 0 and 20. So our random variable can take on any value between 0 and 20. So what does this curve look like in the coordinate plane? F of x equals 1 over 20. Well, that's a constant. It's a horizontal line. So since 1 over 20 is constant, there's no x there. That's a constant. This is a horizontal line. Because everywhere on this curve, f of x, y is equal to 1 over 20. So this is a horizontal line in the coordinate plane. So I'm going to draw this real quick over here, and then we're going to get a nice drawing. So this is x, this is y, and this is 1 over 20. And it goes from 0 to 20. So what this actually is a rectangle. So it looks like this. So this function, f of x equals 1 over 20, f of x equals 1 over 20 is a horizontal line. It's a horizontal line at y equals 1 over 20. The domain of this function, the values that x can take on, that's what the domain is anywhere between 0 and 20 inclusive. So x can be anywhere between 0 and 20. And I think that's all I want to say. And so when we draw this continuous probability distribution function is a rectangle on the coordinate plane. The total area under the curve then would be, how do you find the area of a rectangle? You take the base times the height. And the base here, that distance is 20. The height is 1 over 20. So the total area under this curve is 1. And the probability is also 1. So the area under the curve represents probability. For this probability distribution function, the total area under the curve is equal to 1. All right, just to reiterate, in a continuous probability distribution, the distribution is defined using a function. A function can be graphed on the coordinate plane. The area under the curve, that is the graph of the function, the area under the curve is the probability. The total area under any continuous probability distribution function has to be equal to 1. Okay, so using this continuous probability distribution, can you find the probability that x takes on a value between 0 and 2? So can you find the probability that x can take on any value between 0 and 2? If it's a continuous probability distribution, probability is the area under the curve. So the probability that x can take on any value between 0 and 2 is the area under this curve from 0 to 2. Since this is a constant probability distribution function, the area under the curve is just the area of a rectangle. So you need to find the area of the rectangle that's shaded in purple. And how do you do that? Well, again, what's area of a rectangle? The area of a rectangle is its base times its height. So you find the length of the base, well, that would be 2, correct? And you multiply that by the height. So the probability that x takes on a value between 0 and 2 is just 2 times 1 over 20, which is 0.1. So again, a continuous probability distribution is described by an equation which we can graph on the coordinate plane. And that's this horizontal line right here. That is the graph of this. Described by an equation that we can graph on the coordinate plane. Since this is a constant, it's going to be a horizontal line. And we can find the area over an interval by finding we can find the probability over an interval by finding the area under the curve. The area corresponds to the probability. The probability that x is between 0 and 2 is 0.1, which can be written mathematically as this. So the probability that x takes on a value between 0 and 2 is the probability that x is greater than 0 and it's less than 2. The probability that x is greater than 0 and it's less than 2, or between 0 and 2. And that's the probability that x is less than 2 because our distribution starts. Sorry, I just got a text from my daughter-in-law about my granddaughter, so I got to stop and read them. She started this thing. She's not even 3 years old yet. She goes, "I'm so mad." I said, "What are you mad at?" "I'm mad at Pa. I'm so mad at Pa." That's her grandfather, my husband, or Pa. It was adorable. Anyway, so that's the same as the probability that x is less than 0, because this probability distribution starts at x equals 0 and goes to x equals 20. That's the domain of this probability distribution. So the probability that x is between 0 and 2 would be the same as the probability that x is less than 2, and that is equal to 0.1. The area under the curve between 0 and 2 is 0.1. Okay, so suppose you want to find the area between 4 and 15. So you want to find the probability that x takes on a value between 4 and 15. Again, probability, when you're talking about a continuous probability distribution, is the area under the curve. Now, this is nice and simple because our probability distribution function is a constant. Then the area under the curve is just a rectangle. So it's pretty easy for you to find the probability that x takes on a value between 4 and 15. So you find the base, the length of the base, which would be 15 minus 4, and you multiply that by the height. So the area of this rectangle is 9 times 1 over 20. So the probability that x takes on a value between 4 and 15 would be, did I say 9? I think that's 11. 11 over 20. I think 15 minus 4 is 11, not 9. So the area, 15 minus 4 times 1 over 20 is that area that's shaded in purple. So that is 11 divided by 20, or 0.55. So given this probability distribution, f of x equals 1 over 20, the probability that x is between 4 and 15 is 0.55. All right. Well, now let's define a different continuous probability distribution function. It's still going to be a constant. We're not going to actually look at functions other than constant functions until we get to chapter 6, which is the normal distribution. But say we have a probability function f of x equals 1/8, and x can take on values between 0 and 8. And again, we restrict the values that x can take on so that the area under this curve is equal to 1. So the area under this curve from 0 to 8 would be 8 times 1 over 8, which would be 1. So draw the graph of f of x and then find the probability that x can take on a value between 2.5 and 7.5. So what would this look like? Excuse me. So f of x equals 1/8. That is a constant function. This is constant. 1/8 is a constant. And a constant function is a horizontal line. And the value on the y-axis is 1/8. And x can take on values between 0 and 8. So that is what this continuous probability distribution function looks like. It's just a rectangle whose height is 1/8, and its range, its domain goes from 0 to 8. So what's the probability that x can take on a value between 2.5 and 7.5? So here would be 2.5. And here would be 7.5. So what we're interested in is the area under the curve between 2.5 and 7.5. So how do we find the area of a rectangle? Well, since our curve is a rectangle, our curve is a horizontal line, so our area can be found using a rectangle. It's the base times the height. And our base is going to be what? 7.5 minus 2.5. So that's going to be 5. So the length of the base is 5. And the height is 1/8. So 5/8, or whatever that is in a decimal, 0.625. A much pretty picture in your slides. All right. So suppose we want to find that original probability distribution function f of x equals 1/20. Suppose we want to find the probability that x equals 15. Well, again, you can't do this. Well, actually, the probability is 0 because the width, it's a vertical line at x equals 15, and the theoretical width of that is 0. So the probability that x is equal to 15 is 0. So when you find the probability of x equaling a particular value, exact value, in a continuous probability distribution, that probability is 0. Okay, so in a continuous probability distribution, it doesn't matter if you write less than or equal to or just less than. That is the cumulative distribution function. To calculate x is greater than, then you use 1 minus the less than. So the probability that x takes on a value greater than x is 1 minus the probability that x takes on a value less than x. Just like when we were looking at a discrete probability distribution in chapter 4, if you're interested in finding the probability of a greater than, then you take 1 minus the probability of a less than. Right. So here is an example I came up with. What's the probability that x is greater than 7.5? Now, I think you could just look at this and find the area under the curve is 0.5 times an eighth, or 1/2 times an eighth. So you could do that by just looking at the area. which is 0.5 times 1/8, whatever that's equal to. Take your calculator out and find that. Or you could, I'm going to write this as a 16th for a reason. Or you could take need my eraser. The probability that x is greater than 7.5 is also 1 minus the probability that x is less than 7.5, which would be what? 1 minus 7.5 times 1/8. And you'll find that that is also equal to a 16th. So the probability that x is greater than 7.5, or a half times 1/8, is the same as the probability as 1 minus 7.5 times 1/8. And that is the end of section. Chapter 5, that's all we're doing in chapter 5, is introducing continuous probability distributions. And then we're going to jump right into our various continuous probability distributions. And we're going to look at a bunch of them. And I want to introduce the normal. So I'm just going to start chapter 6, just do a few slides in chapter 6. Because chapter 6 is on the normal distribution, which is our first continuous probability distribution. And this is on your calculator. The normal distribution is found in the distributions in your calculator, so you're not going to actually have to calculate anything as far as integrals go. But I do want to show you what the equation of the normal distribution function looks like, because you go, oh man, am I glad I have a calculator for those. And you can feel sorry for me, because back in the day, when I took statistics, mathematical statistics, we did actually have to integrate this stuff, which, you know, being a math nerd, I found to be great fun. I actually don't recall ever taking a math class I didn't like. I had to take one twice one time. I had to take modern algebra twice. So I dropped out the first time because I was going to fail it. So I dropped out and took it again and made an A. So I persevered. All right, normal distribution. So we're going to first introduce and recognize what the normal probability distribution is and be able to apply it appropriately. So the normal distribution is a continuous probability distribution. So it's a probability distribution defined using a function, an equation, and the probabilities are found by finding the areas under these curves. Now you don't have, like I said, you don't have to do this because your calculator can do this for you. We're first going to talk about the standard normal distribution, and we're going to apply this because there are an infinite number of normal distributions. And when you look at the equation here in a second, you can understand why there are an infinite number of them. And since there are an infinite number of normal distributions, we can take any normal distribution defined by a function, a curve on the coordinate plane, and we can standardize it. And we standardize it in terms of standard deviation. So we'll talk about that probably on Thursday. And then we'll compare normal probabilities by converting to the standard normal distribution. So your calculator can find the area under the curve for any normal distribution, any of them. It can also find the area under the curve for the standard normal distribution. So take a normal distribution and standardize it. It can find the area under the curve, and it'll be the same. Okay. The standard normal distribution. The normal distribution is a continuous probability distribution. So it's a probability distribution that defined by a function, which is a curve on the coordinate plane. And it's the most important of all distributions because it is the distribution that most data that you see will follow. The graph is bell-shaped. So if you ever heard anyone describe a bell-shaped curve, that's a normal distribution. You see it in all disciplines, psychology, business, economics, science, nursing, and of course in mathematics. So for example, shoe size. If you ask enough people, and they do stipulate that you have to ask enough people. If you ask 3 people, this is not going to work. But if you ask 100 people, for example, their shoe size, and then you graph it, the shoe sizes, then their shoe sizes will follow this bell-shaped curve. It will follow a normal distribution. The same is true for heights. If you ask enough people what their height is, and then you graph their heights on a coordinate plane, you will see this bell shape. So much of what we see, what we measure in the world, follows this bell shape. So here is what it looks like. This is the normal distribution. The normal distribution only relies on 2 parameters, 2 numerical descriptive measures: the mean of the distribution and its standard deviation. So every normal distribution curve has the same shape, pretty much, but the shape can be defined by what the mean, or is defined by what the mean and the standard deviation is. So if we have a random variable x, and that random variable is normally distributed, the normal distribution only relies on the mean and the standard deviation. So the way we describe that is this. So capital X is our random variable, and that random variable is described by a normal distribution. So the capital N means it's normal. And the only 2 values that this normal distribution relies on is the mean, the average, and the standard deviation. So when you have this bell shape, we're centered here, and this value that we're centered on is the mean. So here is the function that describes this curve right there. So you see that curve that we have there? See that? It's described by that function. Aren't you glad you don't have to integrate that? So if you were wanting to find the area under the curve between, say, here and here, you would have to integrate that function over that interval. But you don't have to do that. You don't even have to memorize this. But what I want you to see is what are the 2 things that this function relies on. Okay, so x is the input. Remember, x is our input. So that's what you input into this equation. And what do you output? You output f of x. And the only things that we have in here besides x and f of x, well, you have a pi, but pi is a constant. And you have e is a constant. So pi and e are constant numbers. So the only thing that varies here is mu, the mean, and sigma, the standard deviation. So the shape of this thing, what this thing looks like, only relies on what sigma, the standard deviation is, and what mu, the mean is. So that defines the shape of this thing. And so how many normal distributions could you have? Well, you could have an infinite number of them, depending on whatever mu and sigma are. Okay, so that is the equation of a normal distribution. And to find the probability that x takes on a value between 2 values, you need to find the area under the curve. Okay, so a couple more things about the normal distribution. It is symmetric about a vertical line that goes through the mean. Symmetric means the left-hand side and the right-hand side are identical to each other. And in theory, the mean and the median are the same value. So when you have a normal distribution, mean and median equal the same number. And as I said, the only thing that defines the shape of this thing is its mean and standard deviation. As a matter of fact, a little bit of college algebra reminder. So I don't want to get too in depth here, but if you have a function that you've graphed on the coordinate plane, you can change the shape of it. You can make it narrower or flatter or whatever by multiplying by constants. So sigma is actually, the standard deviation is what affects the shape of this thing. So whether it's flat or really steep or whatever, sigma is what does that. And that kind of sort of should make sense to you, because sigma is the standard deviation. Sigma is a measure of how much your data varies. So if sigma is large, you would expect this thing to spread out. And if sigma is small, if the standard deviation is small, you would expect it to kind of compress in. Now, what you're doing in the equation for the normal distribution is you're subtracting mu from x. So you're subtracting the mean from x. And if you remember from college algebra, when you add or subtract a number from x, the input, that shifts it left or right. So the mean shifts your normal distribution to the left or right, and sigma affects the shape of it. Is it flatter or is it narrower? Okay. And then a little history. You can read through this. I'm sure you're fascinated by the history. But the guy that really brought the normal distribution into common usage was Carl Friedrich Gauss. And so frequently the normal distribution is called the Gaussian distribution, named after him. It's been around a lot longer than he was around. It's been used since, way back in the 1700s, but he's the one that really used it quite a bit in showing measurements. And so it gets the name Gaussian. Okay, and that's where we're going to stop for the day. On Thursday, we'll pick up here at the standard normal distribution and continue the discussion of the normal distribution. Are there any questions? All right. Hopefully, we'll see you in class on Thursday in the classroom. Keep an eye on email and text messages for what's happening on campus for the rest of the week. But hopefully, we'll see you in class on Thursday. Have a great rest of your day, guys.